Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your channel Chandan Physics. In this video, we are going to discuss physical interpretation of the wave function psi and its normalization. Let's begin. What is psi? The wave function psi is a solution of the Schrodinger equation, and it provides the information regarding the quantum behavior of that particle. How the particle behaves in that of quantum mechanics, that can be described by that of wave function psi. The wave function, let I prefer psi rt, may represent the probability of finding the particle in time t at a position r with respect to origin. That wave function psi rt may represent the probability of finding the particle in time t at a position r vector with respect to that of origin. What are the conditions in which that wave function represent that one? Basically, we know that psi rt itself cannot have a significance. So, but psi rt, that the wave function itself cannot have significance. Of its own, since it is imaginary. That's why psi rt itself has no significance, but when it is multiplied with its conjugate, it gives rise to the physical significant. What is that of physical significant? Let we assume that the product of psi rt and its complex conjugate means psi star rt, psi rt, its complex conjugate psi star rt, the product of these two gives rise a physical significant. What is that of physical significant? That is the probability density. And it is represented by probability density rho rt. That is probability density in the sense that the probability of finding that of particle in that of time t at position r, that gives rise to probability density when that wave function multiplied to its complex conjugate. That means psi rt when multiplied with psi star rt, that gives rise to probability density, that is magnitude of psi square, which gives rise to rho rt, that is the probability density in the sense the probability of finding that particle in that of region means in time t at a position r with respect to origin, that is the probability density rho rt. Now we have to get therefore the probability of finding the particle the probability of finding the particle at time t at position r vector is the volume element let dv, or we can say it as dqr. What is that of probability of finding the particle? The total probability, that is the probability of finding the particle, will be how much? The probability of finding of the particle in that of dqr section will be how much? That is rho rt dqr or dv, that can be written like this: rho rt magnitude dv, or we can write it as rho rt magnitude dqr. These are the probability of finding the particle at time t at r is the volume element dq or dv here. This is the probability of finding that particle. Now, if the probability of finding the particle is 100%, what should be its representation? Therefore, we can represent the total probability of finding the particle in somewhere in the space, is let 1 means, that is we can say that is 100%, the total probability of finding that particle, that is integration from -1 to +1 psi star rt into psi rt dqr is equal to 1, or that can be further be written like this: integration from -1 to +1, the magnitude of psi rt dqr is equal to 1. That represent the mathematical representation of probability of finding that particle. 1 means the probability of finding that particle is 100%. That is a mathematical representation of psi rt, the physical significance of psi rt. What actually that psi rt represent? That represent the probability of finding that particle when it is multiplied with its conjugate, that gives rise to this one dqr. That means the volume element we consider here. When we consider in one dimension, that is dx will be there, that is a length element. For that of surface element, that is d2x, like this. Since it is we consider volume element, that will be dqr. In that of volume element, what should be the probability of finding that particle? That is represented with the help of this equation. Now, we have to normalize that wave function psi. What should be the normalization of the wave function psi? Now, normalization of psi. What are the equations or what are the procedures through which we can say that wave function is normalized or not? The wave function psi satisfying the equation psi star psi dqr integration is equal to 1 is said to be normalized. This is the equation for normalized. That wave function is said to be normalized when the product of its conjugate over that of volume element dqr integration gives rise to 1. It says that wave function is normalized. If a wave function which is not normalized, it can be normalized to adopt some procedures. Let us discuss that procedure. Let we consider a wave function psi 1. Let psi 1 be the solution of Schrodinger equation, be the solution of Schrodinger equation, then it can be written like this: I h cross del psi 1 by del t, that is the time dependent Schrodinger equation, minus h cross square 2m grad square plus v psi 1, equation 1, with the condition that one is, let psi 1 star psi 1 d square is equal to n, which is not normalized. Normalized in the sense that value will be 1, where n is finite, real and positive. Here that wave function psi 1 is not normalized. Our aim is to normalize that wave function. What are the procedures we have to take to normalize that wave function? How to normalize that wave function? To normalize, this is the condition for normalization. If any wave function is said to be normalized, then it will be satisfy that equation. If that wave function psi 1 is normalized, then it will be satisfy that equation, that means psi 1 star psi 1 dqr will be 1. How we have to normalize that particular wave function psi 1? To normalize the wave function, we now multiply psi 1 by the normalization constant, that is 1 by under root of n, to obtain psi 1 in place of psi 1 we substitute, in place of psi we substitute, that is psi 1 divided by root n. Therefore psi 1 will be root n times of psi. Now putting this in equation number 1. Now putting this in equation 1, we get that will be root n I h cross del psi by del t is equal to minus h square divided by 2m grad square plus v root n psi, or I h cross root n cancel out, I h cross del psi by del t is equal to minus h cross square 2m grad square plus v of psi. Hence equation, let here I prepare equation number 2. Hence equation 2 will be, just substitute, hence equation 2 will be written as integration over root n psi star root n psi dqr is equal to n, or that is n star root n multiplied with integration over psi star psi dqr is equal to n. or root n is a real positive value, that means it will be n root n into root n, it will be n integration from integration over psi star psi dqr equal to n cancel out, that will be integration over psi star psi dqr is equal to 1. Now the wave function is normalized when we substitute psi is equal to psi 1 by root n. Hence we observe that psi 1 by root n satisfies the Schrodinger equation, and psi is equal to psi 1 divided by root n is normalized, that one is normalized. That term satisfies the Schrodinger equation, and in place of psi we substitute psi 1 by root n also normalized, since psi and psi 1 differs by a constant 1 by under root n. These two wave function are differs with a constant 1 by under root n, then n is called the norm of psi 1. Hence n is called the norm of psi 1. Hence we conclude that normalized wave functions have finite norm. Normalized wave function have finite norm. Norm is defined over all space. That norm is defined over all space. It implies that psi at t tends to 0, or we can say that r tends to infinity. The wave function psi, or which can be written as integration over psi star psi dqr exists and gives a finite value. Therefore it will be called as the square integrable. This is all about our normalization and the concept of norm. So with the help of this video lecture we understand what is the physical significance or the physical interpretation of that wave function psi at t. Psi at t gives rise the probability of finding that of particle when it is multiplied with its complex conjugate. This is the probability of finding the particle somewhere else in that of space is 1 or 100%. That means it is satisfy that equation. Psi star psi dqr over that of integration -1 to +1 gives rise to 1. That gives rise to probability of finding that of particle, that is probability density. Then normalization concept, a wave function if satisfy that equation psi star psi dqr over that of integration gives rise to 1, then that wave function is said to be normalized. If that is not normalized, then we have to normalize that particular wave function by proceeding this. If psi 1 is a wave function which satisfies that of Schrodinger equation, but that wave function is not normalized, that means it will not gives rise to 1. We have to normalize that one taking that of procedure. Let me substitute psi is equal to psi 1 by root n, putting that of equation, finally get 1. That means we observe that that particular that is psi 1 by root n satisfy the Schrodinger equation, and also it is satisfy that of normalization condition psi star psi dq r is equal to 1 condition. Then that is differ by a constant 1 by root n, hence n is called the norm of that of psi 1. Hence we conclude that the normalized wave function have finite norm, and that norm is defined as psi r t tends to 0 whereas r tends to infinity, and psi star psi dq r exists and it gives a finite value which is known as the square integrable. This is all about the physical interpretation of that wave function psi and its normalization. So with this useful and informative notes, let me wind up this session. Thank you.